Good afternoon. All right, so let's see here. I just wanted to show you guys, in case kind of slipped under the radar, I did post another assignment. It's just a little multiple choice one again. Same structure as the previous one. It's on chapter 2, which was data and sampling distributions. And I've made it due, I put it in our calendar because these little puzzle pieces don't have due dates from Moodle, they're from somewhere else. So I put it in our calendar. I feel like I made it the night before, yeah, the 9th, because then we said you're gonna have your test 1 is gonna be open on the 10th. So I'm just kind of forcing you to get it done before you write the test, because of course it's gonna be practice for the test, okay? So I'll post one for chapter 3 as well. And then notice how I've got the chapter 4 sections that we're going to work through on Tuesday, but test 1 is only on chapters 1 through 3. Okay? And so there's no meeting on that day. Let's see here. Just done. Bring it in here. Oops. I guess I can crop this a little bit here. This is due March 9th at 11:59 PST. Yeah. And also just notice that there's no meeting on the Thursday, just you can use that time to write the test if you want to. Okay. I've mapped out the rest of the term. This is kind of wishful thinking. We'll see how quickly we can progress reasonably through the material, but I am expecting you to read along and to have read these sections before we meet. Because that way, when I say it, it's the second time you hear it, and then hopefully it just fills in some gaps. Okay, so all right, that's kind of all the administrative stuff I wanted to mention. So for a little bit of review, or more like review, the last little piece that I snuck in was the type 1 and type 2 errors that we could have when we're doing a hypothesis test. Now, just as a reminder, so this is what the review is just the reminder of when we conduct a hypothesis test, and you guys are probably okay if I just abbreviate that as HT, but I'll just write it out once here, hypothesis test, which I always just abbreviate as HT. When we conduct a hypothesis test, we expose ourselves to 2 different types of errors, right? So there's potential for 2 errors that we could be making. And the problem is we don't know which error we're making. Right, and so when we conduct a hypothesis test, we expose ourselves to 2 types of errors. Type 1 and type 2 errors. Now, a type 1 error is the main one that we're going to be concerned with, because it's usually the only one that we can control. Okay, so a type 1 error. And sometimes I find it useful to kind of map these out in quadrants. But type 1 error is when we reject H0, but we shouldn't have. Okay. So a type 1 error is rejecting H0 when we shouldn't have. Let's think about this for a second, right? And so if we consider a normal distribution, for example, because that's probably the distribution that we're most comfortable looking at and comfortable working with, right? So in a normal distribution, for example, then we might have something like this, right? So here's our distribution of things that can happen, right? And we remember that these tails go all the way out to negative infinity and positive infinity, right? So we understand that these tails, anything can happen is what those tails are saying, right? There's a very, very, very small probability, right? Remember the area under the curve, area under the curve is the probability. Okay. So now what we're saying is that, okay, in order to be able to reject my null hypothesis, I force the probability of that happening to be less than 5%, typically 5 or 1% are our go-tos. There are some instances where we might use 10%, but in general, right, let's use the 5%. And I'm just going to focus on one tail. So what did they call it? One way or one, yeah, a one-way hypothesis is what this textbook calls it. I call it one tail just because it emphasizes that we're talking about the area in the tail, right? And so I'm going to focus on a one-tailed hypothesis. And so here, this area is the alpha area, alpha equals 0.05. If we find that our p-value is less than that, right? So our p-value is going to be the area in the tail. Okay. Maybe I should use a different color here. So here, this is our one-sided p-value. Okay. If the p-value, or in this case, the one-sided p-value is, so this is what it would look like if the alternative was that, and without a parameter of interest, I'm actually going to avoid saying that. Sorry. I realized I didn't have a mu or something to talk about. It would be a proportion probably for a z-score, but anyways, doesn't matter. In order to reject my null hypothesis, I'm saying that my p-value has to be smaller than my alpha level. But notice how this 0.05, that can still happen. We're just saying that, well, it's unlikely that it came from this distribution. It probably came from another distribution, right? Which is centered somewhere else. So here, right, this is the area of errors that we could make, right? So notice here, these values could still happen under H0, but are unlikely, right? But are unlikely. Okay. So that alpha level is really going to be the probability of making a type 1 error, right? Because as soon as we reach this threshold, as soon as we have a p-value that's smaller than this threshold of 0.05, which is the default, right? Then we're going to reject H0, right? But there's a 5% chance that we're wrong, right? That it actually did come from, it was just an extreme observation from that distribution, the null distribution. Okay, so this idea of the type 1 error, it kind of haunts us. And so most of our analyses are based around trying to minimize the type 1 error, right? And so we've decided that 5% is a pretty good trade-off, where, you know, we're okay to be wrong 5% of the time, right? We don't know if we are, right? But that's what we've established, okay? And so significance tests are structured to minimize type 1 errors. Right? By decreasing the alpha level. So the alpha level is really, the alpha level is going to be the probability of making a type 1 error. The probability of making a type 1 error. Okay, so you can decrease that alpha level to make sure that you're not going to be rejecting H0 when you shouldn't have, right? And so we can kind of control that type 1 error rate by adjusting our alpha level. Okay. Now, a type 2 error is a little bit harder to deal with just because the type 2 error, if we think about our different options, so if I reject H0 when I shouldn't have, that's wrong, right? So that's our type 1 error. And what if I don't reject H0, but I should have, right? That just means I didn't have enough evidence to reject H0, right? Maybe I should have, but I wasn't able to detect it with the sample size that I had, right? And so type 2 error, oops. The type 2 error is when you fail to reject H0 when we should have, when it should be rejected. This is usually just a sample size issue. Okay. And so usually type 2 errors result from sample sizes that are too small. Results from sample sizes that are too small. Right? There wasn't enough evidence to reject H0, right? There wasn't enough evidence to reject H0, right? So I failed to reject H0 when it should have been rejected. That just means that I didn't have a stable enough distribution to look at, right, to be able to detect that difference. Okay, and so usually the only way that we can control the type 1 error rate is by increasing our sample size. Okay. And so we try to control the type 1, or sorry, the type 2 error rate. The type 2 error rate by increasing our sample size. That's not something that you would do midway, right? You would collect your sample, and there are techniques for figuring out what sample size you need in order to minimize that type 1 error, right? And so, or the risk of type 1 errors. And so, and that leads us to power and sample size, which is at the end of the section. But that's going to be the goal, right? Is we're going to have some difference that we're trying to detect. And so we're going to find our sample size from that, right? What sample size would I need to be able to detect that difference? Okay. So that was an all review, but I'll call it the end of the review because it's what I wanted to finish off talking about last day, type 1 and type 2 errors. And so now we'll pick up on some new stuff. So we did talk about, and I guess maybe not quite yet, sorry. The last thing I wanted to mention, then let me just see here, is just a little point about data science and p-values. And the textbook does a really good job of highlighting the differences between what we learn in Stat 230 and kind of the methods that we learn there, and the difference between data science and Stat 230. So Stat 230 is a course for everyone, and especially, so it's for everyone in the sciences. And so many of those students are going into chemistry or biology or something else, right? And so they need to be able to prove things, academically prove things. So write papers, submit to journals, that kind of thing. And so then we rely on p-values a lot, okay? But for data science, you're going to use p-values as a guide. Was there something that was happening here? But then you're also going to have to use your judgment. Well, is there practical significance here? Or is there just a significant difference that doesn't mean anything to me, right? Did people spend 5 minutes more on my website, or did they spend half a minute more on my website? Maybe I don't care about half a minute. Right? I only care about if they spend 5 minutes more on my website, for example, right? And so there's this idea of, okay, p-values help guide us towards significant findings, okay? But in the end, we're only going to be interested in practical significance, okay? So in data science, we're going to use, so we will use p-values to guide our findings, right? So in order to say that there's a finding, right, of course your p-value has to be small enough, right? So you have to have this idea of, okay, well, because I have a small enough p-value, I can reject H0, right, in favor of HA. So we have to have that understanding, right? But that's not the be-all end-all. We have to incorporate this practical significance as well. So we will use p-values to determine significant findings. So we will use p-values to determine significant findings, right? But we'll also have to use our judgment to determine if those are practical findings, right? And maybe I shouldn't use determine twice. In data science, we'll use p-values to, maybe I'll change this to identify. To identify significant findings, but we will need to use our judgment as to whether the significant findings have any practical significance, as to whether the significant findings have any practical significance. So here, practical significance is, if we can show, so here's an example. So an example would be the p-values show a 1 cent increase in sales, right? But practical if that involves changing a bunch of things and maybe hiring someone to build a new website, that's not practical to me, right? I would want to see a $10 increase in sales, for example, right? Or I might have some idea of what a practical significance would be, right? So a p-value may show a significant difference of, let's say, $1 in sales, in average sales, and maybe I should add that, average sales, in average sales, right? But we have to factor in what it would cost, right? So the cost of implementing these changes to see that $1 change in average sales, and maybe that's too significant, right? Maybe the changes would only be worthwhile if we saw a $10 change in average sales, right? And so, but maybe the changes would only be worthwhile if there was a $10 change in average sale. So if there was a $10 change in average sales. Average sales, I said change, but I should probably say increase, because change means what? It means a decrease of 10 or an increase of 10, but I think we all understand that it should be an increase, right? Or maybe it's a significantly cheaper option, so then it would be a decrease of 10 before we don't implement that change. It just depends on the situation that we're talking about, right? But our job is not just going to be to just focus on the p-values and report the p-values and that's it. Our job is going to be to say, okay, well, you know, the changes that we would have to make to see that change are not worth it, right? So this would not be a significant, practically significant difference for us, right? So, okay. So we've talked about A/B testing, which is when we have group A and we have group B and we want to compare those two groups, right? And so recall A/B testing. A/B testing compares two groups, right? It can be numerical data, so comparing two groups with a t-test, or it can be count data, so categorical data, which would be a z-test for proportions, right? But either way, we can compare these two groups, and that's great. We're going to do that a lot, right? Just comparing two groups. So recall A/B testing, which compares two groups, right? And it can be numerical or categorical data. And so for numerical data, we can compare the means. Compare the means using a t-test. And for categorical data, we can compare the proportions. Oops, categorical data. We can compare the proportions using a z-test. Right? So you'll probably remember doing that. And we could do it using permutations or kind of resampling, or we can do it the old-fashioned way with established sampling distributions. And that's the way that we're used to doing it, right? A t-test or a z-test is with these sampling distributions. So we could use resampling instead, but here let's just go back to our roots and what we're familiar with, right? So a t-test or a z-test, okay? But what if we have just 3 groups? Yeah. So now, right, A/B testing is good if you're only concerned about comparing 2 groups. But as soon as you introduce another group that you might be interested in, that's not that wild, right? Maybe you have the layout of website 1, and then the layout of website 2, and then the layout of website 3. That's not that crazy, right? And you want to test which one performs the best by some metric, right? And so now we have more than 2 groups that we want to compare. Now, one thing that you might just want to do is you might just want to compare, okay, A, B, and AC, and then BC, and then you've done those 3 comparisons and you've exhausted all the options, right? So what if we have, more than 2 groups? Like A, B, C. Let's just focus on A, B, C for now. Okay. Well, we can do pairwise comparisons. Oops. We could consider, and I highlight could because there's a better way to do it. We could consider pairwise comparisons. So A to B, which is the same as B to A, right? So order here doesn't matter. A to B, A to C, and B to C. The problem becomes we open ourselves up to a type 1 error every time that we do this, right? And so that means that there's a 5% chance of a type 1 error here, 5% here, and 5% here, right? And so I've increased the probability of making a type 1 error. So it's inflated. So it's not 5% anymore. It's, I think, 15. I can't remember the math. Anyways, so I want to say it's not that, but anyways, doesn't matter. So we introduce, or we expose ourselves. We expose ourselves to type 1 errors. Oops. To type 1 errors with each comparison. With each comparison. Okay. So there's a couple of ways that we could deal with that. Okay. In fact, there are many ways to deal with that. But I would suggest that if you had to do these pairwise comparisons, I would probably just use a Bonferroni adjustment, which means that you're just going to divide your alpha level by how many comparisons you're making. Okay, and so there are many ways. Oops, I meant to underline many, not are. There are many ways to adjust to making multiple pairwise comparisons, right? So there are many ways to adjust for multiple comparisons. Yeah. But the simplest way, and there's lots, like I said, there's Tukey's honest significant differences, but I think the easiest way is the Bonferroni adjustment. So there are many ways to adjust for multiple comparisons, but the simplest is the Bonferroni adjustment. It's fun to say too. The Bonferroni adjustment. which says that your adjusted alpha is the original alpha divided by the number of comparisons. Right, so for these three pairwise comparisons, I would do 0.05 divided by 3. So for example, for alpha equal to 0.05 with 3 pairwise comparisons, I would use an adjusted alpha of 0.0167, let's say. It's 6 repeating, but let's just draw the line at kind of reasonable number. Okay, so instead of using 0.05 at each test, right, the only change that I would make here is that I would use an alpha level of 0.0167 instead at each turn, right? And so now I'm exposing myself to the same amount of type 1 errors, right? But it's been divvied up among the comparisons. Okay. So let's see here. This is a good spot. So they talk about degrees of freedom, but let's just parking lot degrees of freedom. And because I want to lead us into the ANOVA procedure, so the analysis of variance. And because what happens if I have, let's say, five groups that I want to compare, right? I could go through and list them all, A, B, A, C, A, D, A, E, right? So what happens if we have 5 groups, right? So A, B, C, D, E, right? Just listing all those comparisons is going to be really annoying, right? And so we could list all these comparisons and do them all, but you can imagine that, especially if you're doing it all by hand, so think before computers, especially then, that wasn't very efficient, right? So, okay, what can we do? All right, so we could list out all the pairwise comparisons or all the pairs, right? But let's say we have 10 groups or 10 treatments that we want to compare, right? Then all of a sudden, I really don't want to do that anymore, right? I don't want to list out all the pairs and then run all those tests. And also my alpha level is going to be really small, right? And so we could list out all the pairs. But what happens is the more pairs that we're looking at, right, the more plausible it's going to be that one of those is going to be significant, even if there's not a truly significant difference, just by variability and, you know, how randomness works, right? There's going to be a significant difference just by random chance alone, right? And that's what we're trying to avoid, right? We're trying to highlight the differences that are truly random, truly different, right? Not just by random chance. So we could list out all the pairs and with computers, running the comparisons isn't that hard. Running the comparisons is not hard, right? But now think back to before computers, right? So think back to before computers. And then think about how nice it would be if there was, so if you had 5 groups or 10 groups, if there was a test that we could run, kind of a simpler test that we could run with less calculations, which just allowed us to kind of look in to our experiment and see, hey, is anyone different in here, right? Or are you guys all the same, right? If you guys are all the same or not significantly different, then there's nothing to report here, right? And so it's, I kind of imagine just kind of opening up a box and saying, hey, is anyone different in there? And then your test tells you that, yes, there is something that's different in here, so it's worth exploring, right? Because then you know that listing out all these pairs and running these tests is going to yield something, right? But if I look into this box and I'm saying, hey, is anyone different in here? And the test tells me that no, nothing different here, then why would I bother going through and listing out all the pairs if I've already run a test that says, you're not going to find anything, right? And so that's where the ANOVA comes in, this analysis of variance. And we use it in a couple of different contexts. We use it to compare means, so multiple means, more than 2. We can also use it to compare coefficients in regression, which we haven't really talked about yet. So I'll kind of parking lot that for chapter 4. But there's lots of things that we could use an ANOVA for, but those are the main ones. Okay? And so so think back to before computers and imagine having a test, you could run before considering all the comparisons. So before considering all the pairs, that would tell you if you were going to find anything or not. That would tell you if you would find anything or not. And by find, I mean find anything significant or not. Right? This is the ANOVA. This is the ANOVA, analysis of variance. And we saw it ever so briefly in Stat 230, but now we're going to spend a little bit more time on it, a lot more time actually. So the ANOVA, what's interesting about the ANOVA is that it looks at the variance within each group, right? So how much variability am I expecting in each of the groups? And then it looks at the variability across the groups. And then, so it's really hinging on the variability, but the variability is the difference between the means and the data points, right? So kind of similar to what we've seen before, but so it takes the variability in each of these groups, and then it says, okay, well, how much variability do I have across the groups? And visually what it's going to look like is if you have box plots, side by side box plots, if you have kind of boxes that are shifted off of each other, they're more likely to be significantly different from each other, right? Significantly different groups. Whereas if you have groups like this, so just focusing on 2 groups here, my eyes to my mouth, they're the same, right? But as soon as I shift these up, then those would be probably significantly different, right? Because there's no overlap here. Even if there's a little bit of overlap, right, they might be significantly different. So, okay, so this is the analysis of variance. I kind of, it's not a test that's going to tell you what is different. It tells you if there is something that's different in there. Okay, and so one note about the ANOVA, oops. it considers multiple groups. Considers multiple groups. Okay. And will yield a significant p-value, right? So a p-value that's less than 0.05, right? So it's going to run this thing called an Ftest, and it's going to consider multiple groups and will be significant if there is a pairwise comparison that's significantly different, right? So if there's anything going on in there, so considers multiple groups and if there is anything going on, so, and I'll kind of clarify in brackets here, anything going on means if there is a pairwise comparison that would be significant. So a significant pairwise comparison. It will return a significant p-value. It will return a significant p-value, which means the p-value is less than the alpha level. And we're back to 0.05 for that alpha level by default. Depends on how expensive the changes would be that you would have to make, or how dangerous they are, right? So of course, if you're testing a vaccine, some unknown vaccine, then you're probably not happy with 5%. You would probably decrease it to 1%, I hope, in order to say that it affects us significantly, but maybe not. Okay, maybe we're happy with 5%. I don't know. I haven't read any studies. That's bad of me, right? But I just trust that they know what they're doing. Okay, so the thing about the ANOVA and kind of what leads you astray is that it's only going to tell you if there's anything going on, right? But to figure out what is going on, you need to do those pairwise comparisons still. Yeah. So I think of the ANOVA as kind of a gatekeeper, right? If the ANOVA says there's nothing going on, why would I keep going and consider those differences? That's just foolish. What a waste of time, right? And so, okay, so let's just, I've got a fresh page here, so it's going to look weird for a bit here, but I am going to highlight the ANOVA again. And what I didn't say is multiple groups of numerical data. Okay, and so the ANOVA compares numerical data across more than 2 groups. Now, it can do 2 groups, but I don't really see the point, because then we could do a t-test, right? So that there's no, and they would be very similar, right? But a t-test is kind of easier to wrap our heads around, and it tells us if there's a significant difference between the 2. So I would just go for those 2. So I'm going to say for more than 2 groups. So compares numerical data across more than 2 groups. Okay. And how it does it is by using an F statistic. So if I say, so the equivalent would be here, I'm running an ANOVA. If I run a t-test, then I calculate a t statistic, right? The test statistic is t, and I just am lazy and I call it a t-test. But for an ANOVA, what an ANOVA uses is it calculates an F statistic. So it's a capital F. And I'm pretty sure we've seen it, but I'm not remembering where or when. right now, but that's okay. And so an ANOVA calculates an F statistic So an F statistic measures, so this is where I was saying, okay, it looks at the variability within each group, and then it looks at the variability across the groups, right? So just in general, how much variability do I have and how much variability do I have within the groups? And that's going to tell me if there's anything going on here. Okay? It's to me, especially in the beginning, it just kind of felt like magic or kind of witchcraft. But I mean, it works, and the more you kind of work at it, the more it'll make sense. Let me move my calculator here. So the F statistic measures the extent to which differences among groups or group means to which differences among group means exceed what might be expected in a chance model. Now, a chance model is the hypothesized, the null hypothesized model. Okay, so it measures the extent to which differences among group means exceed, oops. What might be expected in a chance model, right? So the null hypothesis or the chance model is the H naught, which in this case is that mu1 is equal to mu2, which is equal to mu3, which is equal to mu k, right? Allowing for k different groups to be compared. The mean of k groups, and those means are all the same, right? Not significantly different from each other. Okay, that would be the chance model. So yeah, these groups, the sample that we're looking at, yeah, they look a little bit different, but there's no significant difference among them, right, that we can detect. Okay. So transitivity to me would mean the transitive property, isn't that like A plus B plus C is the same as A plus C plus B? You'll have to clarify for me. No, so that's the problem with the ANOVA, is that it won't tell you what's going on. Okay, so the ANOVA, the alternative hypothesis, let's highlight what that would be. The alternative is that at least one mu I does not equal mu j. So it doesn't tell us, right? I keep doing these blocks, but notice it does not tell us which pairs. Awesome. And good question. Thank you. I'll have to brush up on my properties. Transitivity is an inequality property, I guess. Anyways, doesn't matter. Thank you. And so this is the problem with the ANOVA. It's the beauty of the ANOVA, but it's not where you end, right? So once you have enough evidence to reject H naught that they're all the same, then all you really know is that there's something worth finding in there. And then you would go and you'd look at these pairwise comparisons, but then you at least know that you're doing it for a reason. Okay. So it's kind of a weird thing, but it makes more sense if you imagine yourself back in, I think hypothesis testing has been kind of established from 1920 or so. I think I was reading, and so you can imagine then it was nice to have this kind of test, right? Well, is it worth doing or what? So many calculations. Remember, for each t comparison, you would have to find the standard deviation of each of the groups, right? Just doing that by hand is painful, right? You'd have to have the means, you'd have to have all this kind of stuff, the pooled standard error. It's been a while, right? So you would have to calculate all those for each of your groups, and it's just a lot of work that you would have to do if you were doing it strictly by hand. Okay. So sometimes we talk about one-way ANOVAs versus two-way ANOVAs. I think it's my job to just kind of tell you that there's no real difference between the two. A one-way ANOVA just considers, you know, numerical data across some number of groups, whereas a two-way ANOVA breaks it up, right? So maybe you have the average commute time on weekdays, and maybe you have the average commute time on weekends, or maybe in March and January. And so the difference between a one-way ANOVA, so a one-way ANOVA really just compares groups over one factor, and maybe I should say compares numerical data. Oops. Compares numerical data, usually the means, right? Across groups of one factor, groups from one factor. And it's just that one that makes the one way. Okay. So for example, right, average commute times over the days of the week. Over the days of the week. That's one factor, right? The day of the week is categorical: Monday, Tuesday, Wednesday, Thursday, blah, blah, blah. And so, and maybe we just focus on the weekdays, so Monday through Friday or something like that. Whereas a two-way ANOVA would consider another factor, right? So two factors. So whereas a two-way ANOVA and I'll wait to highlight, compares numerical data, does the same thing, but across groups from two factors, across groups from two factors. Oops. Okay. And so, for example, right, we could build on this average commute time over the days of the week, and we can compare summer months to winter months, for example, right? And so we could consider the seasons or by the month or something like that, but we introduce this second factor that we're considering. Okay, so the two-way, the average commute times over the days of the week as well as, and broken up by the season, let's say, and broken up by the 4 seasons. Right? So that's that second factor that we can consider. Okay. Highlight this, stick 2. Hey, it's lagging. I had to check that I wrote it. I did. Just took a while to show up. Okay, so we have talked a lot about degrees of freedom in these different contexts, and we've used degrees of freedom in the t-test. And I keep saying stuff like, don't worry about what it is, just take n-1, or the smaller of n1 minus 1 or n2 minus 1, or it's the number of rows minus 1 times the number of columns minus 1 for a chi-squared, for example, right? But there's all these degrees of freedom mentions, and we never really get to the bottom of it. And we still won't, but I'll give you a little glimpse as to what it is. But in general, we're just going to need to keep just using these degrees of freedom. But it does help to have an understanding of what it is. And they are really kind of weird to wrap your head around, right? And so that's why I want to introduce it. But if you just keep going the way that we have been and just understand that most of these distributions require degrees of freedom to determine the shape, right? Think about the t-test, right? If I have a small sample size, then the tails are kind of wide or thicker. And as I increase my sample size, it becomes closer and closer to the normal distribution, right? So we understand, we already know that the degrees of freedom dictate the shape of the distribution. Okay, and so and that's really all we need to know. So far, we have seen that degrees of freedom are used to determine the shape of a sampling distribution. Degrees of freedom are used to determine the shape of a sampling distribution. Yeah. And that's really all we need to know, right? But where it comes from is the number of values that are free to vary given some information. So for example, if I'm doing a t-test, right, then I am testing one mean, for example. Okay. So consider a t-test, a one sample t-test. Which analyzes the mean, analyzes one mean X bar, right? Then we know that the degrees of freedom is going to be n-1. Okay, why is that? Well, here we go. The degrees of freedom are the number of values that are free to vary. The number of values free to vary. Okay. So going back here, why is it n-1? Well, if I have the average of 10 values, right? So if we let, for example, let n equal 10, right? I have 10 values. And if we know X bar, right, then the first 9 values, 10-1, are allowed to be whatever they want, right? But if I have to arrive at a certain X bar, then the 10th one is fixed. right? It has to be whatever forces that average to become what we've said it's going to be, okay? And so if we let n be 10, then we know, then we know the degrees of freedom is n minus 1, which is 10 minus 1, which is 9. Okay? Which means that if we know x bar, this means if we know x bar, the first the first 9 values, right? And this is the same 9 as the degrees of freedom. The first 9 values are free to vary. Are free to vary, right? Be whatever they want to be. Okay. So those first 9 values, they can be anything, right? And then to adjust for what they are, then the 10th value is not, it's fixed, right? Because we know what x bar is, so we know what we have to accomplish. And so that 10th value has to be the value that forces that x bar, right? And so, so the first 9 values are free to vary, right? But the 10th must be the value that gives us the x bar. But the 10th value must be the value to give the x bar, right? So it adjusts for all those free range values, right? So here I'll say not free to vary. So that's the idea behind degrees of freedom. And it's going to come up later where, you know, we might have a table, so an R by C table, so the rows by the columns. And from the chi-squared tests that we've seen, we can calculate those a little bit differently depending on the tests that we're running. But in general, it's the number of rows minus 1 times the number of columns minus 1. And that gives us our degrees of freedom. So the number of rows, right, if I know the R minus 1 of the rows, then, and I know the total, then I can adjust that last one and I can figure it out, right? So then I have R minus 1 degrees of freedom in the rows and then C minus 1 in the columns. And it's the same idea, right? It's basically how many things can I let change before I have to have them fixed, right, in order to achieve what I want, right? A total that I want or an average that I want or something like that. Okay. So like I said, degrees of freedom are hard to wrap your head around. I know that. And so for us, maybe we're okay with just, and this doesn't say Sam, pling there. Right, so maybe we're okay with just here's the degrees of freedom, right? But as you get more comfortable with it, right, you can come back to this definition of the degrees of freedom and maybe it'll make a little bit more sense. But honestly, as long as you know to use them, you're fine. Okay. Okay. Let's talk about, so we've focused on numerical data. What can we do for categorical data, right? So now categorical data is usually involving counts of some sort. right? And so the most common test that we do, as soon as we have more than two groups that we want to compare, so as soon as we have more than two groups, and even with two groups, we can use a chi-squared, right? So to compare counts from more than two groups, to compare counts across groups, right? Usually more than two groups. But what we'll find is that the Z test for comparing two proportions that we've used in the past, it ends up, and even in the R code, I think they just use a chi-squared test anyways. So they're very similar for the two groups, so it just depends on what you want. But to compare counts across groups, usually more than two groups, we use a chi-squared test. We use a chi-squared test. Right, so this is the Greek letter chi, and it's spelled chi, but you'll people will laugh at you if you say chi, so you have to say chi. Like that. Okay. Otherwise, people will laugh at you, and I don't want that. It's a chi-squared test. Okay. So the chi-squared test, most often what we're using it for, and there are many different tests that we could use a chi-squared statistic for, just like a t statistic, we can use it to compare one mean to a hypothesized value. We can use it to compare the mean difference to some value, usually 0. We can use it to compare two groups, right? The mean from two groups. So that t test statistic is, we can apply it to many different things. Same thing with the chi-squared. We can test independence. We can test goodness of fit. We can test the homogeneity, I want to say, and probably some others. But what we're going to focus on is independence. So especially, you know, if you're comparing our shopping habits for women, is it independent from those of men, or does it depend on what your gender is for how many times you shop on Amazon, for example? Right, that kind of thing. So now we're talking about independence across groups. And so the most common use for chi-squared tests is to test independence, across groups. So really what we're saying is, so I have these counts across some categories, and I can look at one category, or I could have, I could consider two categories, right? And I could split them up in a table like this, the counts. And that's very similar to what we just saw in the numerical case. But so to test independence across groups, what we're really doing is we're comparing the observed counts to the expected counts, right? So if these two groups are independent, then we would have some expected count across the groups, right? And then we compare the observed counts that we saw, right? They're not necessarily all the same, but maybe they're all within some realm of the same, right? Not significantly different. And so then I can just go ahead and call them all the same, or at least not significantly different. So what we're going to do here is the chi-squared tests count data to see how well oops, how well it fits some expected distribution. Some expected distribution. Yeah. Now, this expected distribution comes from the null hypothesis, right? Our hypothesized distribution. So this is the H naught might be that if the groups are independent, then the counts would be equally distributed across the groups, right? So maybe I'll write that out here. So this is from the null hypothesis, which for independence, right, the counts in the groups are even, which really just means not significantly different, right? They're not exactly even, right? But they're independent of each other. Okay, so the counts in the groups are even or not significantly different. Right, but I'll put even in brackets because if you're looking at 200 observations and you have 4 counts in one group and 5 counts in another group, they're not the same, but they're probably not significantly different, right? Out of a group of 200, even if you had, 14 people here and 16 people here, those probably still aren't significantly different. So for chi-squared tests, we usually have 1 or 2 groups, right? But typically we have 2 groups. So for tests of independence, we can consider data from 1 or 2 groups. We can consider data, and maybe I should clarify counts. Counts across 1 or 2 groups. Oops. Okay, so if you have 1 group, right, maybe with A, B, C, D options, right, then you would have something like this, right, A, B, C, D. And then you have your observed counts. And then you'd have your, and maybe I'll write this out better. And then you would have your expected counts. So from your hypothesized value, right, if we have an observed count of 4, oh, sorry, I should do 14, 21, 19, and 15, right? Then my total here is going to be 14 plus 21 plus 19 plus 15 is 69. So then across 4 groups, if they're evenly distributed, then, so if that's my hypothesis that they're evenly distributed, which is usually what we would do. So then what we're saying is, okay, if they're evenly distributed, then there's really no significant difference between being in group A, B, C, or D, right? So think about these as, you know, packaging design A and B and C and D, which ones were picked the most. Okay, so then I could divide this 69 over 4 options and they would be evenly distributed. 69 divided by 4 is 17.25. So I would expect 17.25 in each category, and I'm allowed to have fractions in there because they're just expected counts, okay? And so I would just flesh it out over however many categories I have, and then I would have these observed counts and the expected counts, and my expectations come from my null hypothesis. So, or if I have, and maybe I'll scoot this over here. So here's one group. If I have 2 groups, and then it might look something like this. Now, I'm not going to show you the math here because we're not going to do it by hand, right? But maybe I have A, B, C, D over yes and no categories. Losing my voice here. Right, so now I have this some number of rows and some number of columns. So R is the number of rows and C is the number of columns. And this is what we call an R by C table. Okay, you always read it as the rows by the columns, and oh my gosh, I think I'm out of time. What? Okay, that's okay. We'll pick this up, but this will be on your first test, which is on Thursday, right? So you might not want to wait until I introduce this, the remainder of this on Tuesday, but I will finish it on Tuesday. So you might want to read ahead a little bit, but other than that, I'll see if there's any questions, but if there are no questions, then I hope you have a great weekend, and I'll post a lab. Now I know how far we've gotten. I'll post a lab for tomorrow that you can work through, and I hope you have a great weekend. I'll see you on Tuesday.